All right, let's talk atoms. Have you ever really thought about how we figured out what they look like? I mean, you can't see one. So in this explainer, we're going to trace that incredible story, piece by piece, to see how the modern picture of the atom was built. And then we'll look at what happens when that atom's core gets a little unstable.
Okay, so here's what we've got on tap. We'll start with Thomson's first sketch of the atom, then see how Rutherford totally changed the game. After that, we'll dive into Bohr's wild new rules for electrons, decode his model, and finally, we'll get into what happens with an unstable nucleus. We're talking decay.
All right, let's kick things off. Our story starts way back in 1903 with a guy named J.J. Thomson. This was basically the first real scientific attempt to draw a picture of the atom.
So Thomson had just discovered the electron, which is a huge deal, right? And he thought, okay, I know atoms are neutral. So his idea was this. The atom is just a blob, a sphere of positive charge, and stuck inside that positive goo are these little negative electrons scattered all around, kind of balancing things out.
And this idea got a fantastic nickname, the plum pudding model. Now, if you're not from the UK, you might be like, what's plum pudding? Just think of it like a chocolate chip cookie or a blueberry muffin. You've got this big positive dough, and the little negative electrons are like the chocolate chips or blueberries scattered inside. Simple, right? But you know, this simple model had some big problems. First, it couldn't explain why different elements glow with very specific colors when you heat them up. It's like each one has its own unique color barcode, and this model had no answer for that. And the second problem, the real deal breaker, came from an experiment. When scientists shot tiny particles at a super thin sheet of gold foil, some of them bounced straight back. That should have been impossible. It'd be like shooting a cannonball at a piece of tissue paper and having it ricochet back at you. And this is where Ernest Rutherford enters the picture. That crazy gold foil experiment? That was his. And its results didn't just poke a hole in the plum pudding model, it blew it to smithereens and forced everyone to come up with a totally new structure for the atom. So, based on those ricocheting particles, Rutherford came up with a wild idea. He said the atom must be mostly empty space. Yeah, almost nothing. He figured all the positive charge and pretty much all the mass had to be crammed into this incredibly tiny, dense little ball at the center, which he called the nucleus. And the electrons? They were way, way out, orbiting that nucleus like planets around the sun.
This became known as the planetary model, and it was a total game changer. I mean, think about it. We went from a featureless blob to this miniature solar system. The atom finally had a structure, a center. It was an elegant, beautiful idea. It's a great picture, right? It explained the gold foil experiment perfectly. But there was a huge problem. Actually, two of them. According to the physics everyone knew at the time, this kind of atom shouldn't even be able to exist.
Okay, problem number one, the death spiral. Classical physics says that an electron whipping around a nucleus should be constantly giving off energy. And if it's losing energy, it's slowing down. And it would spiral right into the nucleus in less than a blink of an eye. Poof, no more atoms. Problem number two was that light spectrum thing again. If the electron is spiraling in, it should be emitting a continuous smear of light, like a rainbow. But that's not what we see. We see those sharp, specific barcode lines of color.
So the planetary model was in big trouble. To save it, a physicist named Niels Bohr did something completely radical. He basically said, well, maybe the old rules of physics just don't apply inside an atom. He took this brand new, bizarre idea called quantum theory and came up with 3 new rules just for electrons.
And these rules were wild. First, he said electrons can only exist in certain special, stable orbits. And when they're in one of those orbits, they just don't radiate energy. They break the old rule. Second, he said there's a specific mathematical condition for which orbits are allowed. It's all about something called angular momentum. And third, the only time an electron emits light is when it jumps from a high-energy orbit down to a lower one. It's not a gradual spiral, it's an instantaneous leap, a quantum jump.
Okay, so with these new rules, Bohr wasn't just guessing anymore. He could actually do the math. He could calculate the exact properties of these special orbits, and this led to some incredibly powerful predictions, especially for the simplest atom of all, hydrogen.
So first up, the radius of the orbit. What he found was that the radius grows as the square of this number n, which we call the quantum number. What does that mean? Well, if the first orbit has a radius of, say, 1 unit, the second orbit isn't at 2 units, it's at 4 units. And the third is way out at 9 units. These energy levels get spaced out really fast.
Now this part is kind of counterintuitive. You'd think an electron in a bigger orbit would be moving faster, right? Nope, it's the other way around. The velocity is proportional to 1 over n. So the electrons in those tight, low-energy orbits are zipping around like crazy. The ones way out in the higher orbits are actually moving much slower.
Okay, and what about the energy? You'll see it's proportional to -1 over n squared. Now, don't let the negative sign freak you out. All it means is that the electron is trapped or bound to the nucleus. You have to add energy to pull it away. So a bigger n means a less negative number, which just means the electron has more energy the farther away it gets from the center.
And here's the payoff, the absolute triumph of this model. When Bohr put all this math together, his predictions for the spectral lines of hydrogen were perfect. They matched the experimental data exactly. You can see it right here in this diagram. Every time an electron drops to that second energy level, boom, it spits out a photon of visible light. When it drops all the way to the first level, it's a higher energy ultraviolet photon. It just worked. So Bohr totally nailed the problem of the electrons, which was a massive win for quantum theory. But that's all about what's happening on the outside of the atom. Now we need to shift our focus to the very center. What happens when the nucleus itself is unstable? Well, that's when we get radioactive decay. The basic idea behind radioactive decay is that it's all about probability. You can't predict when any single atom will fall apart, but you can say that the rate of decay for a whole chunk of material depends on how many atoms you have. The more radioactive atoms you start with, the more decays you'll see every second. It's kind of like making popcorn. At the beginning, lots of kernels are popping, but near the end, it slows way down.
And this graph shows you exactly what that looks like. See how steep the curve is at the beginning, on the left? That's when you have tons of atoms, so the decay rate is high. But as time goes on and you move to the right, the number of radioactive atoms goes down, and the curve gets flatter and flatter. The rate of decay slows down because there's just less stuff left to decay.
Now, there are two key terms we use to describe this process, and it's good to keep them straight. You have the decay constant, which is lambda. Think of that as the probability of decay for a single atom. It's a measure of how unstable that atom is. Then you have half-life, which is probably the one you've heard of. That's just the time it takes for half of your sample to disappear. One's a probability, the other's a clock.
All right, let's do a quick recap of the key formulas we've seen. We've got Bohr's rule for angular momentum, that's what decides which orbits are allowed. Then the Rydberg formula, which is the one that predicts those exact spectral lines. We've got the law of radioactive decay, telling us how many atoms are left after a certain time. And finally, the simple little formula that connects half-life to that decay constant.
But that leaves us with one last big question. Bohr's model was an absolute masterpiece. For hydrogen, a single electron orbiting a single proton. But what happens when you have more than one electron? Now things get complicated, because those electrons are pushing on each other. And solving that puzzle, well, that would require a whole new chapter in physics, the leap into full-blown quantum mechanics.